Hello, I'm Michael Coblenz. I'm a fourth-year PhD student at CMU in the computer science department. This is collaborative work with a bunch of people, including Elliot Canal over there. Maybe raise your hand so people know who you are. I want to talk about a new programming language that we're developing for blockchain programming environments. But before I do that, I want to explain what blockchains are, since they're a fairly new computational environment. The idea with a blockchain platform is to support shared global state on a distributed system. So imagine you have several partners that are collaborating and they want to do transactions, let's say banking transactions, for example. But they want to do it in a way that's resilient to attacks that may compromise some of the peers. So these systems are composed of a collection of servers, we'll call them peers, and some of those may be compromised because an adversary may have taken control over one of them. And we want to run programs on these systems. These programs are typically called smart contracts. So I'll be using that term, smart contracts, which just means program in this context. So when we have a program, a smart contract running on a blockchain, what we can do with it is we can invoke transactions. So think of a transaction as some kind of operation that can happen on a program running on a blockchain. Now these programs are stateful. They record information about the state of the world, and a transaction can modify the state. So in particular, a transaction can deploy a new contract, or it can invoke existing code in an existing contract. Now, there's this principle that they call code as law. And the idea is that code, you can think of code as specifying some kind of agreement between parties. So the clients that are doing transactions on the blockchain have signed up for whatever the implementation on the blockchain is. So if there's any problem with the program on the blockchain, let's say there's a bug there, well, there's no other authority who anybody can go to. It's just the implementation is the implementation. And furthermore, if there is a bug, because programs on the blockchain are immutable, there's no way of fixing these bugs. So it's particularly important in this context that we be able to write software that is correct. So just to give a very small example of a blockchain, here's a very small 3-block blockchain. Each block consists of several transactions put in a sequence. And in addition, there's a key value store that has the state of all of the contracts, so you can easily look up the current program state. Why might we be interested in blockchains? Well, the DoD has a variety of proposed applications for blockchains, including healthcare records, supply chain, logistics, resilient communications, and cybersecurity. Just to drill down in one of these, if you imagine a supply chain example in which you're assembling a system from a variety of components, and you're worried that maybe one of the components was produced by a vendor that is producing fraudulent parts. And maybe you've gotten word that a particular vendor has been compromised, and you'd like to know what are all of the systems that have a part from this vendor. And you're also worried because this vendor has been compromised, maybe your information tracking the supply chain has also been compromised. So by putting all of this information in the blockchain, you secure yourself from a variety of these kinds of threats. So why is there a problem here? Well, the problem is that existing blockchain programming approaches are vulnerable to attack. So over $70 million have been stolen over the past year or so from various blockchain contracts due to bugs in those contracts. And because those bugs can't be fixed after deployment, this is particularly a big problem. So we want to build correct software, but the current ways we know of building software have resulted in these vulnerabilities. So our approach here is a new programming language that we're calling Obsidian. We're taking a user-centered and domain-centered design approach in designing the programming language. And our goals here are to make some kinds of vulnerabilities impossible, and also to make it easier to write correct programs. We don't want it to be very difficult to write all programs. We want to make it easy to write correct programs and hard to write incorrect programs. And we want to show that this is the case by showing that people can effectively write software with our language, and also that we have actually guaranteed the safety guarantees that we're promising by a formal analysis. So we're using two kind of main approaches to design this language. The first observation is that a lot of blockchain applications are very stateful. So we're using a technique called type-state-oriented programming in order to lift a lot of the state information into the type, so that the compiler can actually reason about these properties. There's evidence that this kind of approach is helpful when people are reading documentation. We want to also show that it's helpful when people are writing code. The second approach is the observation that a lot of these contracts govern important resources. And resources should be thought of differently than typical objects in an object-oriented system. Take money, for example. When I give you money, I no longer have the money. That's very different from a traditional reference-based approach in which if I pass you a reference to an object, well, we both now have a reference to the object. So here there's some static notion of ownership that the compiler can enforce. So if I try to spend some money, that's fine. But then if I try to spend the money again, the compiler can give me an error. I don't have that money anymore. I can't spend it again. So I want to show a little example here. Here, first of all, we're saying that money is a resource type. So we have this resource contract money. And we have a bond contract. Think of this like a financial bond, like a bank might or a company might issue. So a bond can be sold, and once it's sold, well, it can't be sold again. That's how this kind of bond works. So a bond is always in one of two states. There's the offered state and the sold state. When it's created, it's initially put in the offered state. And in the offered state, there's a buy transaction that is available. You can see here in the scope of the offered state, there's a buy transaction there. And the buy transaction's implementation, if you see in the second line, will transition to the sold state. And then if we look in the sold state, you can observe that there is no buy transaction available in the sold state. Again, once it's been sold, it can't be sold again. So how do we take advantage of this in a client? Well, here's an erroneous client on the right side that creates a bond, and it's statically of type bond.offered, because that's how all new bonds are. And someone can buy the bond once, but if we try to buy it again, we get a type error from the compiler. So we're detecting this error at compile time. If we were doing this in Java, for example, you'd typically have a method that was available in all states, and then you'd have some code that checked at runtime dynamically what the state of the object was. So you wouldn't find out until runtime that there was any kind of problem here. One of the important parts of our approach is that we're taking a user-centered approach to the design. You could imagine we could design this language by disappearing into a cave for a few months and then coming out with a language. And in addition to the language, there's a big manual. And I tell everybody who's supposed to use the language, here's the manual, good luck. But we are taking the perspective that a programming language is actually an interface that people can use to write software for computers. And as such, it's subject to the principles of human-computer interaction. And so we're taking a human-centered approach in the design and working HCI approaches into the design of the language. And in particular, rather than waiting all the way until the end to do some sort of evaluation, we're actually working in user studies all the way through the design of the language. So we're evaluating fragments of the language and prototypes of the language with participants in user studies to see which approaches are most natural for people and which approaches lead people to write code more quickly and more correctly. Initially, we designed a language formalism and a surface syntax for the language. We implemented a compiler that translates our Obsidian code to Java. So far, we've completed one round of user testing just in a text editor. One of the approaches that we're using here is called a natural programming technique. And the idea is we want to find out how people would naturally write particular kinds of code. We can't necessarily just design the language that way. That might be a little bit naive to just ask people to design our language for us. But we do want to take people's natural inclinations into account so that we can design a language that matches people's expectations. So we've looked into the syntax and semantics of state transitions and into one aspect of resource types. We can talk about that later if you're interested. We're revising the language based on the results of those studies. Currently, we're looking at evaluating approaches to permissions. Permissions are an approach to address aliasing situations when you have many references to the same object. When you have many references to the same object, you have to worry about which references actually carry state guarantees and which don't. And one of the novel approaches in this is brought about by one of the difficulties in evaluation. If we were to hand a user a copy of Obsidian and ask them to do some programming tasks, and we're trying to evaluate some aspect of Obsidian, well, that would be very difficult because we would first be asking the person to learn Obsidian, which is a new programming language to them. So instead, we're evaluating particular elements of the design in isolation by backporting them to Java. So we can take people who already know Java and evaluate particular design aspects in the context of Java. Then eventually we'll do a summative study and hope to show that people who use Obsidian result in programs that are less buggy and can do so faster than if they were using an existing language. So in summary, although blockchains offer a promising approach to various kinds of security problems, current approaches at programming them have resulted in bugs. So our approach is to design a new programming language in which people can reason more easily and more effectively so that they can write code more successfully. So thank you very much, and I'm happy to take any questions.
So is this more of a, oh, that's on. Is this more of a guidance, or does it have control? Is it a true programming language? Control structures, data structures, operators, functions, and such, syntax, or is this an overlay and an advisory piece? Because it's a hard sell to get millions of installed, billions of installed base systems to convert to from what's out there.
So a lot of the blockchain platforms support multiple programming languages. Our approach at the implementation for now is to write a compiler that translates to Java. So any blockchain platform that supports Java, in principle, could run Obsidian programs. So that's kind of the approach. Obviously, people would need to learn Obsidian in order to write programs. Hyperledger Fabric, for example, actually runs programs in a Docker container. So you just need to be able to build a Docker container. So you wouldn't need the entire world to port everything to Obsidian. We just need to build containers that work appropriately on a particular platform. Does that answer your question? Okay.
So I guess I'm wondering if there's third-party type blockchain references or nested ones. So if I inject your bond, I do the central blockchain to say I want to put a buy or I want to go in there, and then the transaction happens, and my bank account or whatever is also a blockchain. Do I have a third-party operation that can reify the results of that thing, or does that have to be resolved in some out-of-band way?
Yeah, there's a whole separate problem regarding the transactional semantics of cross-blockchain operations. So for now, we're assuming that we're working on one blockchain. There may be many contracts on that one blockchain, but when we invoke a transaction, we can actually have transactional semantics because there's one blockchain that we're talking about. At some point in the future, yeah, I think that'll be an important issue to address, and I think that's something that the major blockchain platforms are starting to think about. I'm not sure that there are really good answers there yet.
I guess the other kind of obvious question is, all right, we have the reason for this language is to avoid the bugs in the blockchain programs. How do we avoid bugs in your compiler?
Yeah, that's a good question. I mean, there are lots of techniques that are used in research in order to build verified compilers. That particular angle is not my research direction. So the compiler that I'm building is more of a prototype compiler rather than a verified compiler. But the answer to the question, how do we know that the compiler is right, I think ultimately is build a verified compiler.
Which you're okay with. That's somebody else's work, but you're good with it.
Right,
okay.
right. And there are verified compilers, for example, for C.